Hi, I'm Kiana Ehsani from University of Washington. Today I'm going to talk about my joint work with Facebook AI Research, CMU, and UIUC on predicting the physical forces in human-object interaction. How can we define understanding a video, in particular the human-object interaction? One might say that it is labeling the observed action. For example, in this video, a skillet is being lifted. However, if the goal is to imitate the observed action, simply recognizing the verbs is not enough, and it requires a deeper physical understanding. We need to know how the skillet was grasped and what are the forces that are applied to it. In this work, the goal is to, given an RGB video of a person moving an object, predict the observed contact points on the object and the physical forces applied to it on each frame. We do this through a novel technique that learns to do so without explicit forced supervision. Our key insight is that the supervision can be indirectly obtained by simulating the effects of the predicted forces in a differentiable manner in a physics simulator. Next, we describe the dataset and our proposed formulation. To train our system, we collect a dataset of videos recorded from multiple participants grabbing and moving objects. This dataset represents a diverse set of objects from YCB where an accurate mesh of objects is available for use. We collected 13,000 frames of 174 different interactions with 8 known objects. One possible way of obtaining labels for training is to attach expensive noisy force sensors on the object, but this limits the interaction and might make it unnatural. Instead, we collect annotations in the form of 2D locations of semantic key points in each frame. We then calculate 6 depots of the object with respect to the camera in each frame, though these are noisy due to partial visibility and coplanar key points. And finally, we recovered the 3D contact points on the object mesh for each interaction video from 2D contact point annotations in camera frame. Note that we do not have force supervision in this dataset. Our model predicts the contact points on the object given the RGB input video. We then use the initial state and the image features extracted from the observed video to predict the forces for each frame. The implied effects of these forces can then be recovered by applying them in physics simulation. Using the feedback from the environment and the updated states, our model learns how to change the forces accordingly and even make up for the mistakes it might have made along the way. To allow learning the model end-to-end, we require differentiable physics simulation. While the typical physics general-purpose simulators are not differentiable, since the number of input variables in our scenario is low-dimensional, we can use the finite difference method to calculate the gradients of the outputs of the simulation with respect to its inputs. We train our model by optimizing for 2 objectives. First one is an L2 distance that optimizes the predicted contact points to be as close as possible to the ground truth. And the second one indirectly enforces the imitated trajectory in the physics simulation to be close to the one observed in the video. We apply the predicted forces on the object and get the updated state in 3D simulated world. Then we transform the 3D key points on the model back to the camera frame under the simulated rotation and translation. By minimizing the discrepancy between the ground truth key point annotation and the reprojected ones, we get the feedback on how to update the forces and parameters of the model. Note that the annotations for contact points and key points are our only supervisions here, and we do not have force labels. Our experiments show that we can predict meaningful forces from videos whose effect lead to accurate imitation of the motions observed, and more importantly, by jointly optimizing for contact point and force prediction, we can improve the performance on both tasks in comparison to independent training. Here are some examples for which our model makes better contact point predictions when it gets the feedback from interacting with the object. And finally, we showed that we can learn a representation from this model that generalizes to novel objects using only a few shot examples. For this experiment, we trained the model to learn how to apply forces on a toy airplane and use that to generalize to predicting forces on a different object using only 1 to 10 examples. Thanks for listening to this talk, and here's the link to the code and data for this project.